Hello, and welcome to my Lab 1 presentation, the amount of excess charge on an ordinary object. My name is Anand Jha. Let's begin. To introduce this lab and to state its main purpose, this lab is to show us how matter can be temporarily charged by either removing or adding electrons to the atoms that compose that matter. We also calculate the effect charged objects have on neutral objects, aka objects with a net charge equal to zero. Finally, we will calculate the net charge on a piece of Scotch tape in coulombs. Some fundamental principles that this lab will cover will be Newton's first law of motion, which states that any object experiencing a net force equal to zero will stay in uniform motion, Coulomb's law, which states that the electrostatic force equals kq1q2 divided by r squared, where k is a universal constant. We also realize that like charges repel while opposite charges attract, an idea that can be seen in magnets. We also hopefully see that neutral objects are attracted to charged objects as they experience what we call dipole moments. So to describe the actual experiment, we plan on creating two electrically charged pieces of Scotch tape. And we will make one of these pieces of tape be suspended in the air by counteracting its gravitational force with the repulsive electrostatic force. We will then determine the electric charge on each piece of tape, and using that we will calculate the number of electrons lost or added to the tape. Finally, we will calculate the ratio of the number of electrons lost or added to the number of atoms present. So some assumptions that we make in order to properly conduct this lab is we will assume that the charge on both pieces of tape are equal once they reach equilibrium. We also assume that the charge on each piece of tape can be treated as a point charge centered on the middle of the tape, as this makes it a lot easier to use Coulomb's law. We also assume that gravity and the electrostatic force are the only two forces acting on the tape, at least in the y-axis. We also assume that atoms are perfect squares in order to properly calculate the number of atoms present on each piece of tape. So some background info for this lab is the fact that the charge of an electron is equal to about negative 1.6 times 10 to the negative 19th coulombs. Also, the mass surface area density of Scotch tape is about 0.0666 kilograms per meter squared. Also, the length of an atom is about equal to 1 times 10 to the negative 10th meters, and the gravitational constant here on Earth is equal to 9.81 meters per second squared. So moving on to the data and our observations made in the lab, we recorded the dimension of each of our pieces of tape was about 0.019 meters by 0.127 meters. This allowed us to calculate the mass of the tape, which was about 1.6 times 10 to the negative 4th kilograms. We also observed that our piece of tape, the U tape, was positively charged as it attracted a negatively charged plastic pen. We also observed that our tape floats or is suspended when the distance between the two pieces of tape is about 0.0125 meters. So using our data and observations, we can create our calculations and the final results for this lab. So first, we need to know the gravitational force acting on the piece of tape, which is just equal to mg, which is about 0.00158 newtons. From there, we can set that equal to Coulomb's law to calculate the charge of the tape, which is about equal to 5.24 times 10 to the negative 9th coulombs. Using that, we can calculate the amount of electrons that are missing from each tape by dividing it by 1.6 times 10 to the negative 19th. That gave us about 3.28 times 10 to the 10th electrons that were missing from each piece of tape. To calculate the atoms present on the tape, we simply took the area of the tape and divided it by 1 times 10 to the negative 20, which gave us a total of 2.413 times 10 to the 17th atoms present. Finally, the ratio of the deficient electrons by the atoms present on the tape was about equal to 1.36 times 10 to the negative 7th. We also used GlowScript, a Python programming language, to model this experiment and to continuously change the distance at which the pieces of tape start floating. This can allow us to calculate the charge required on each piece of tape to suspend it at that set distance. In the picture here, the bottom green sphere represents the center of tape A, while the top green sphere represents the center of tape B. The red arrow is the repulsive electrostatic force, while the blue arrow is the downwards gravitational force. We can see that each tape has equal net charge and that the two forces cancel each other out to create a zero net force. So in conclusion, we saw that about 1 out of every 10 million atoms lost an electron, which is a fairly small number. But just by 1 out of 10 million atoms losing an electron, we saw that it was able to counteract the gravitational force, meaning that the electric force can easily counteract gravitational force as it is much, much stronger. Some additional questions to answer are, what if electrons had positive charge while protons had negative charge? In this lab, the end result would have been the same, except we would have determined that our pieces of tape were negatively charged or had a net negative charge instead of a net positive charge. Also, why is it important to handle the charged tapes as little as possible? This one is just to make sure that the electric charge doesn't get reset back to zero, as any interactions with neutral material such as our skin or our bodies can make it so the piece of tape reaches equilibrium and gets reset to a net charge of zero. Thank you for listening to my presentation.